Hello everyone, and today we're going to be talking about path planning. But before we get into path planning, we need to talk about graph, because a lot of the search algorithms we're going to be using are done on a graph. So to start off with, what is a graph? So a graph is just a collection of edges and nodes. So people either refer to these nodes as vertices, so a lot of times we'll see denoted by V, and E will denote your edges. So I have nodes, which are essentially, you can think of them as discrete states. Each one of these dots is going to be a node, and then edges are how we connect these different things. A graph can be a collection of any number of nodes and any number of edges. You can have fully connected graphs where every node has an edge to every other node, or you can have a very sparse graph where there's maybe only one or two connections per node. So there are a couple properties about graphs. So edges can either be directed or undirected. And what that means is that if I have two nodes and I have a directed edge, that means I can only traverse from A to B. I cannot traverse from B to A. Now you can have directed graphs and undirected graphs. In undirected graphs, it's essentially just a shorthand way of writing that I have two directed components, one that goes in the forward direction and one that goes backwards, so I can go from A to B and B to A. You can also have edges that connect to the same node, so I have this node B here. I can have an edge that connects back to itself. And this will be really important when we start doing search algorithms. This represents the idea of doing nothing. If our robot just maintains the same position, maybe we just stay in the same node. So when we're talking about nodes and what places you can reach from a given node, we have this thing called successors. So a successor is the node I can reach using edges from a node V. So if I have my node V, and it has a couple edges going off like this that all go to different nodes, which are like nodes A, B, and C, the successors of node V is every place I can reach by following an edge from V. So I also have predecessors, and this is essentially using edges in the reverse order. So we would say that the predecessor of A is V. So you probably notice even on a really simple graph, where I just have one node that is connected back to itself, I can have these things called cycles. Now you'll typically want to avoid cycles in the graph theory sense because it gets a lot more complicated to prove certain properties about things. So a lot of times we work in this system called DAGs, which is directed acyclic graphs. These means that we have a graph and it has no cycles. So if I have some nodes and I have edges that connect these nodes, there's no way for me to go around in a loop infinitely. Now, a lot of times in robotics, we'll end up with graphs that do have cycles. So that's something we're going to have to learn how to handle. So I've kind of been talking about graphs, but the question is, why are graphs relevant to what we're doing? So what we can do is we can take a grid like we used in week 5 when we did our occupancy grid mapping, and we can represent this as a graph. We can then use pretty standard graph search algorithms, find a way to get from some start grid to a goal grid. So let's say I have this is my start grid, and this is the goal that I'm trying to reach. So if I'm starting at this start location, the way I can build a graph is I have my start location, and let's say I converge to this grid cell or this grid cell, and you can do that by creating edges and then creating two new states here that would represent those grid cells. And I can just keep doing this, building it over and over and over again. And what this allows me to represent is how can I transfer from one grid cell to another grid cell. Now you notice that I only connected the diagonals, and the reason I didn't connect these black diagonals is because those are obstacles. And I can say that that's non-traversable. Now you can keep iteratively doing this process over and over and over again. What eventually you'll do is you'll get a graph that represents the entire state space. So we'll have every one of these squares will be represented by a node in our graph. And every place I can go that is valid, where there are no obstacles, will be represented by an edge. And then what I can do is I can just search on this graph that I've created, and I can find what is a valid path that doesn't go through the obstacles. So I can get something that looks like that. And since I've planned in this graph, I can then convert it back into this grid, and I can use path tracking like we talked about in week 7 to follow my trajectory there. This is what you're going to be doing in this week's exercise. The graph generalizations that are really important is the fact that we can discretize a continuous space. So that's what we did in this prior example here. We really have this robot that can be anywhere on the XY plane. We discretize that XY plane to discrete cells and then represent the occupancy of each grid cell, and then say there is a valid edge if two grid cells are adjacent and one is not an obstacle. Now our nodes represent our state, so this could be lifted into 3 dimensions or higher dimensions. Think about this in the general definition of state. Anything we can represent in our state in, we can discretize, and then search over using these algorithms. And we can also represent our actions. So before I talked about actions where I can go from two adjacent grid cells, so I can go from here to here, or here to here, or here to here, or here to here, but a lot of times you can also represent it as you can move in all 8 directions, but there are different ways you can represent actions, and each one of these creates an edge. Now, it would make sense that you want to create actions that connect all the different grid cells together, and what you'll get is a very densely connected graph, but there are a couple issues with that we're going to talk about in a later video. But that's the basics of graph. We have these vertices that represent our generic state definition, and we have edges that represent our general control definition. That's all for this video, though.